work today that I'm going to talk about is done by Medagarda and myself and two postdocs, Hongxi Wu and Xiahao Chen, who have done a lot of work on the transient absorption and a lot of collaborations with different experimentalists doing this. And I want to call out Phil because we started thinking about this while we were on sabbatical visiting Phil. I realized I had forgotten this, and you might really not know where Louisiana is. You've probably heard of Louisiana at some point, and when you think of it, you think of that it's sort of an exotic locale, sort of very special scenery, and that turns out to be exactly true. It is a very, very special looking place. It's somewhere near my house, actually. So you should visit sometime if you can. So what I'm going to talk about is this using, trying to do strong field physics using attosecond pulses and precisely synchronized laser. So I'm going to look at, again, having an attosecond XUV pulse and the synchronized laser field, and doing these coupled solutions to try and actually learn something, but also get close to connection to experiments. And we've done collaborations with 3 different experimental groups over the last few years getting results on this. Steve Leone's group in Berkeley, Ursula Keller in ETH, and Giuseppe Sansoni in Milan. And then we've also had a collaboration on macroscopic reshaping of attosecond radiation with Arvinder Sandhu, who is local. Is he here today? He was here the other night. He's at the University of
He's coming. He's coming.
Okay. He's coming. Well, you tell him I mentioned it. I did my duty.
There is the video.
So, well, it's impressive if he's coming up today. So the idea here is that the attosecond pulse, which is short, a few hundred attoseconds long, is precisely synchronized to somewhere within the IR laser pulse, which is maybe, this one is about 7 femtoseconds long. So again, the half period of the IR laser is about 1,300 attoseconds. So this is a small fraction of that, and a small fraction of the overall period. And again, the idea is that some infrared laser pulse got split in half. Half of it went off to make harmonics, which by the tortuous process we discussed, or one of the tortuous processes that we've discussed over the past few days, is made into an XUV pump, either a single pulse or a train. And that is used to pump some sample, and the rest of the IR pulse is used as a probe, and there's a delay that can be controlled. And so the idea of any transient absorption is to try and characterize the polarization that can be made transiently in a medium by a pump pulse. So the idea is you kick something, you dump some energy into some system, and then you want to come along later and see, a basic question would be, is the energy still where I put it? Like, has it decayed? Has the system returned to its ground state? Stuff like this. Those are not exactly the questions we'll ask in these studies, but that's the general idea, is that you can study transient polarizations that you induce by pumping a system. And it's, by definition, these excitations are not going to last forever. So you look at it as a function of delay, you get some idea of what's going on. And so here's sort of the really basic idea. The idea is that I would have these 2 pulses, and they have some delay between them. So here's the IR pulse now, and I don't have the little wiggles. And here's the attosecond pulse. And I pass this through my material. And on the back end, I have a spectrometer, and I look at how much light got transmitted through it. And assuming I had, for instance, initially a smooth frequency distribution in my pump pulse, some frequencies are missing here. So some light has been absorbed. And if I look at the difference of what I put in and what I took out, then I get an absorption signal. And so the idea is, here's one delay, and here's one absorption spectrum. And here's a different delay, and here's a different absorption spectrum. Okay? And what you do is you put all of these together on a plot where delay is going this way, and frequency is going this way. And one of these delays gives rise to a spectrum, which is a thin slice here. And then you do this. Then you do this at many, many different delays, and you build up a spectrogram. Yes?
Sorry, I'm confused. So is the IR the probe or the pump? Is the IR the probe or the pump? Sorry.
I don't know.
No.
As in, I don't actually have to know. So that's too quick an answer, but the spectrum of these two pulses don't overlap in any way. One is centered at about 1 eV, and one is centered at 20 to 100 eV. So it's very obvious that the XUV pulse is going to do the excitation out of the system, because we're going to keep the intensity of the IR laser low enough that it's not going to pump the system out of its ground state. So that would clearly say that the XUV is the pump and the IR is the probe. However, you could also take the view that, I mean, once the electron is excited, the IR pulse is going to do a lot to it. There's going to be many orders of nonlinearity around. So that looks kind of pumpish as well.
So why does the probe go first?
It doesn't have to.
Okay.
We're going to look at all of these, all of the possible delays. And so that's what's been done here, is all of the possible delays. This is a calculation that's actually done. I'll talk about it more or less throughout the whole talk. This is done for helium atoms, and the attosecond pulse is about 300 attoseconds long. It's the 7th attosecond pulse. But my point here is the thing that you get. This is the spectrogram. So let me push the button. Yes?
What's the absorption spectrum? It's in IR range or in the...
No, it will turn out that this is in the XUV region.
Oh, okay.
So we're going to look at how much of the XUV light gets absorbed or not. That's what we want to know. In principle, you could look at the IR, but you've got a lot of IR photons, and you don't want to be aiming them at your spectrometer. So, I mean, it would take filters and things. But this is dead simple, because the XUV pulse is not strong. So that's what we're going to look at. So what you get out of this is a spectrogram, which is a thing that you take by stitching together many, many different spectra taken at a set delay. Okay, so it's very important that we understand that the coordinate down here is delay, not time. Okay, and that means that the resolution that I see in my spectrum is going to be set by parameters of the system. In other words, how fast does the polarization decay, or if what's the gas pressure, what's the dephasing time, all sorts of things like this. It is not controlled by any kind of uncertainty principle. And that's because we measure the result of an entire experiment without knowing what happened at any given time.
In this schematic, what does the transient refer to?
The transient would probably, in this, would refer to the fact that the features, the size of these features here is directly tied to when the system was pumped with respect to when the IR pulse ends. So in other words, there are features here that are only there if the two pulses overlap. And in that sense, it's transient. But it's a very, very good question. So really, the central task is you have a transient absorption spectrum, and it encodes for you some ultra-fast dynamics. So this spectrogram encodes the dynamics in the system, but not in a way that's maybe completely obvious. Right? I mean, you can think of this as an encoder, and somebody has a decoder trying to do the experiment. Yeah. One more click. And so here's another way to think about what's going on. I've chosen a particular delay where the attosecond pulse comes along during the envelope of the IR pulse. Now, in the situation that we're talking about, the XUV pulse is going to start all of the dynamics. So there's nothing happening here because the IR pulse doesn't excite the system. But once it gets excited, then we have a very fast polarization response, because now we have something in a high-lying excited state, something in the ground state, right? and the two beating against each other will give you a very fast polarization, basically at the frequency difference between those two states. And so that's the very fast green stuff here. And also the IR pulse will induce linear or nonlinear processes between the excited states, and this will give rise to a slower modulation of the overall signal. So there's an underlying fast polarization signal, which just has to do with the fact that you've excited the system. And then we come along and we mess with that polarization. We amplitude modulate it by using the IR laser to couple it to other states in the system. And so here is really the picture you want to keep in mind. You've got the ground state. The excited states are sort of 10 eV or more away. It's the XUV pulse that does this excitation. Then you have states, excited states that are 1 eV or less apart, and the IR laser moves them around. So in these sorts of experiments where you keep the IR intensity moderate, and we discussed the other night how an IR intensity that can't excite the system can still look like a really strong field to the excited electron, right? It will find itself above the barrier and all sorts of things like that. So the XUV starts the time and the IR induces the dynamics. And so it's the IR-induced dynamics that we want to study this way. And so this is just like AM radio. You have a carrier signal, which is the fast polarization that was started by doing this excitation. And then you have a modulating signal from coupling these states together with the IR laser. And this gives rise to an overall polarization, which is very complicated. And this is, of course, what goes into Maxwell's equation. So this is something that we were kind of thinking about the other day, so I realized that we have this movie. So here's a very simple example of the kind of thing that goes on. So just consider 3 low-lying levels in helium. I've got the 1s, or I should say 1s squared state, the 2p state, and then I've got an IR laser that is tuned so it kind of couples the 2s and the 2p state. So all throughout this talk, I'm going to talk about bright and dark states. It's kind of a very dangerous thing to say in a room with quantum opticians because they have, I think, different meanings of dark states. But what I mean by a bright state is one that's accessible by the XUV laser from the ground state. So those are the kind of states you could see in synchrotron spectroscopy. You know, they're one photon. They have one photon matrix element to the ground state. So they're bright because they can be lit up by the XUV laser. The states like the 2s over here that are not directly coupled to the ground state, they're dark for me. They're dark because the XUV laser the XUV pulse can't light them up. So anyway, we have an XUV pulse and it's going to be here and it's going to excite some population in the 2p state, and then the IR pulse is going to come along and couple that to the 2s. And there's going to be a plot here of just the excited part of the wave function. And so as time goes along here, you see first we make this 2p state, then the IR pulse comes along and messes with it. And we're left with a superposition of 2s and 2p that's going to oscillate then forever after I show this again. So early on there's nothing. Then the XUV pulses come. At this delay, it makes just a 2p state. And then the IR pulse comes along and couples that 2p state to the 2s state rather strongly. And so then it can make a superposition of these two states. And it leaves the system in a superposition state. So like Tony was talking about yesterday in the calculations that Robin Santra had done where they started in a superposition of 2 different things. This would be one way to do it. But from the transient absorption point of view, what this combination of 2 states does is it leaves the system with a complicated time-dependent dipole moment. So now you can see it again. You see the initial wave packet gets made and then modulated and then left.
What is the lifetime of the 2p state? The spontaneous lifetime?
Excuse me?
What is the spontaneous lifetime of the 2p state?
Really long.
Okay.
And so the lifetimes and the line widths and all that stuff in the experiments and in the calculations are way, way shorter than those. Okay. So that's something we're going to discuss. What is absorption? Basically, if you get nothing else out of this talk, you're going to be able to at least parrot my answer to what is absorption, which is absorption is an interference process. Okay? So that's what we'll get to. So here's again our favorite slide where we talk about we can solve the one atom Schrodinger equation for we have some light field or fields here, right? This will be the combination of the IR and XUV lasers. This is, for instance, something that describes helium and far below the doubly excited state, so this is a one electron superpotential. You calculate a polarization by calculating the time-dependent dipole for the whole pulse, then Fourier transforming it, and that's your polarization. And then that's what goes into the space marching form of the Maxwell equation that we talked about that ignores the backward propagating light. So this is the fraxial approximation for the light envelope. So what is absorption in time? You're probably used to thinking about absorption of light in terms of a cross-section, right? So the system will absorb this frequency. The system won't absorb that frequency, right? How does that happen, right? And one thing I want to say is it can't happen by photons, okay? Not for us, because we've got a bazillion photons, and we know that the Maxwell equation description of this system is essentially perfect, right? And so we have to be able to get absorption and emission, as we talked about the other day, out of this coupled equation treatment. So what is absorption in that picture? And so if you have a time-dependent picture of absorption, here's sort of how it looks. So again, let's just say, how does XUV light that is more or less resonant with this 1s2p transition, how does that get absorbed in a sample? Okay, how do I think about that? And in this treatment, single atoms alone by themselves don't absorb any light. All right, it takes all the atoms working together to actually absorb the macroscopic amount of energy from the pulse. So here's what happens, that when the XUV pulse comes in, there's no IR pulse now for a little while. The timing of the initial excitation is well defined because you have this really short XUV pulse. And so you start a dipole ringing at this frequency difference. So here's the dipole ringing with a period 2 pi over this resonant frequency. And this excitation is, in the approximation that there's nothing funny going on, and these are just two normal bound states, this excitation is exactly out of phase with the driving field that made it. Okay? And that comes out of first order perturbation theory, and the time-dependent Schrodinger equation, or however you want to do it. So this is ringing. It's out of phase with the field. So it's going to make a polarization that's going to contribute to a new generated field, which is out of phase with the field that made it. Right? And so now these two fields will be able to interfere destructively, and energy will disappear from the beam overall. Now, in this time domain picture, so we have here that the timing of the initial excitation is well defined. It's out of phase with the field that made it, so we have the possibility for destructive interference. But here's another wrinkle in this. To see absorption, we have to impose, nature or us or somebody, has to impose a time scale for decay or decoherence of this dipole ringing. In other words, it's got to run down over some amount of time. Otherwise, this rings forever, and the dipole Fourier transform of it will be a delta function. So all the energy will go into a frequency bin of 0 width. All right. So there's always something that provides a time scale, ultimately, for the system to lose this phase coherence. Okay. We do not need the population to go back to the ground state. That doesn't happen. Doesn't need to happen. We just need this dipole to decohere so that the dipole response of the system goes to 0. And so then we get a frequency response with a finite width that can be seen in the spectrometer and can be calculated before the end of the universe. This time scale, it's independent of the pulse durations that you're putting in. That's the important part. It's an external time. So it is imposed by At the very longest times by spontaneous emission. In normal experiments, it's imposed by the gas pressure, the atoms running into each other, all sorts of effects. In our calculations, we impose it. We impose a window function on the dipole so that it eventually runs down. But we make sure that that time window is longer than all of the times that we're interested in the experiment, so that it would give features that are narrower than all the features that we see in the spectrogram, which are due to actual dynamics that we're interested in. So here's one way of thinking about how absorption happens in this picture. I like this. I stole this from one of ours paper. So think about that. I have a very thin layer of gas, and I have some field going in that has a distribution of frequencies. And maybe the frequencies don't all arrive at exactly the same time. So this is a chirp. There's a very thin layer of atoms here laid out in a 2D array. And what do I see after the gas? Well, after the gas, I have the field that went in, and I also have a new field that got generated because I made a polarization in the medium. And the generated field, you can show, is proportional to the time derivative of this polarization. And so in the frequency domain, this time derivative introduces an I, factor of I, which is the pi over 2 phase shift that we need for the generated field to be out of phase with the field that made it. So now if we look at the light that's coming out, let's just say, what is the spectral density? In other words, how much energy per unit frequency is there in the light coming out? Well, you would get that by multiplying some factors times the spectral amplitude of the pulse squared. So this would tell you roughly how much, not roughly, this would tell you up to a constant factor how much energy you had at each omega. Because the field that comes out is the linear superposition of what went in and what got made, it looks like this. There's 3 terms. Here's the energy per unit frequency that we put in. And here is an interference term between those 2 things. And out here is a field just due to the generation. This is like high harmonics. This is what we talked about the other day. This is a very low order process compared to this one in what we're doing, because we don't have enough intensity to make any high harmonics. So the only game in town is this interference term between the generated and the input field. And this can be either positive or negative. If it's negative, it's going to subtract energy at a given frequency. If it's positive, it could add energy at a given frequency. And the whole point of the kind of calculations that we're doing and thinking about is that the IR laser can redistribute the energy that the medium has gotten from the XUV laser over the bandwidth of the IR, and actually outside the bandwidth of the IR using nonlinear processes, but over the bandwidth of the XUV laser. So in other words, you have an XUV pulse that's, say, 5 eV broad, and then the IR pulse can do energy redistribution within that 5 eV envelope. Yes?
So is energy conserved here?
Yes. So the energy that comes at, in other words, the energy that goes into exciting the system and making this polarization will get pulled out of the field.
I know in reality that's true, but
In the calculation, yeah, the way that they're coupled.
Even though you put in by hand this artificial decay of the dipole?
Yeah, because that's not, so that's only going to determine how the energy is distributed in frequency, but not the absolute amount of it. And so my artificial decay, or the real decay in an experiment, and by the way, this sort of thing will come from the spectrometer resolution as well, right? So the spectrometer resolution is equivalent to, and so the resolution is often not that great, and so it can be equivalent to a few hundred femtoseconds damping time. But my point is that the features in the spectrum that the artificial window induces are narrower than all of the real features that we want to look at. So, and we're okay. But do you understand my answer? I'm not cheating, right? The window function is just determining sort of the width of the features, but not the absolute amount of what goes on. So it really is true that you can, the XUV goes through and it causes ionization, and that causes excitation, and that will pull energy out of the field downstream. you see how that goes. So this is really, I mean, you either buy this or don't, but this is the interference term between the generated field and the input field. And this is what is going to add or subtract from what I put in. So again, there's always two time scales involved. So for instance, again, let's just think about this 1s2p absorption, right? There's the duration of the pulses that are driving the whole process. Then there's the duration of the calculations, or the resolution of the spectrometer used in the experiment, something, right? It's not always us. And so we wanted to have a finite duration. So what happens? So here, for instance, is the frequency spectrum of an input pulse, which is actually about 60 femtoseconds long, and sits on top of this 1s2p transition. And so the dotted line is the initial spectrum. And this thing with a hole in the middle of it is the spectrum that makes it through the gas after you're done with the calculation. And so this looks like absorption, right? I mean, you lost energy right at the resonance there, all right? But notice a couple of things about this, not least of which is that if you have a long medium, and once you've absorbed all the energy there is at a certain frequency, you can't keep absorbing it, right? You do this in a coupled way. So you can't just keep pretending that the system, that more energy can be eaten. Now, this is not to say that we have saturated the absorption, all right? Most of the atoms in the gas are still in their ground state. It just means that we've used up all of the energy that we sent in at a given frequency range, right? And so then this will start to spread. Right? So this, yes?
Just to be clear, I mean, you don't have an IR pulse here. It's just the
I don't have an IR pulse. This is hard enough.
XUV and the propagation
Yeah.
of the medium.
That's right. And this is already kind of messing with our head a little bit, right? Not pulse. I mean, a lot of people, this is very well known, but I mean, it's still a nice thing to learn. So this mimics the experiment. So, and this is really important. If you see a sharp frequency feature in the spectrum, right, in your spectrum that goes through the gas, and again, everything here is happening in time and then gets Fourier transformed at the end. If you see a sharp feature, you know that in time, that corresponds to a really long time scale, right? So if you have narrow absorption features in your gas, it has to somehow generate long time behavior in your fields that go through. And that's actually what happens. So if you look, for instance, in this calculation, here is in time the envelope of the input XUV field, and these are femtoseconds. So it really is about, I don't know how long it is, it might be 30 femtoseconds long. If you look at the envelope of the pulse that goes through the gas, it has this basic shape like the pulse we put in at the beginning. But the polarization that gets produced, which is out of phase with the driving field, makes this long tail. And so there's this long time feature that gets added to the electric field as it goes through the medium that gives you this sharp absorption feature. And it has to be that way because there are just Fourier transforms involved. And I'm not allowed to talk about photons or anything like that. Do you still give out Willis lamps?
He never gave me a license.
Right, so I don't know if you know this story. Willis Lamb, who was at the University of Arizona for many years, famously said that, you know, you never needed, or almost never needed to actually refer to photons to explain anything. And that if he felt that it was really, really necessary for somebody to discuss something in terms of photons, he would grant them a license to do so. He said he had about a half a dozen such licenses in his desk, and he couldn't remember the last time he gave one out.
Never got one.
Yeah, and Pierre never got one, so certainly not getting one. So we have to do it this way. Right. And so what do you see? Again, there's no IR pulse. What do you see as you go through, right? Here's this pulse which is very broad in frequency compared to the resonance that we're looking at. So here's the XUV pulse before propagation. It's a short thing with a few cycles in it. And now we're going to have it propagate through the gas. And so what happens after it propagates through the gas is it gets this long tail dragging behind it. this long tail is oscillating at this 1s2p frequency, and it's out of phase with the stuff up here. And so at the frequencies that are in this tail, you're going to get destructive interference, and you're going to see less